Vamos allá. Good morning, everybody. Welcome for a new IAA colloquium from the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the presentation by Dr. Giuseppe Morello from the IAC. Good morning, everybody. Welcome for a new IAA colloquium. There is an echo. From Dr. Giuseppe Morello from the Instituto de Astrofísica de Canarias in Spain. And he will talk about a holistic approach to exoplanet spectroscopy. So now Dr. Morello will be properly introduced by Isabel Marquez. Please, Isabel.
Thank you, René. Good morning, everybody. Thank you very much for being here or online in this new Isabel Ochoa colloquium. Today we have the pleasure of having Dr. Giuseppe Morello. So thank you very much for having accepted our invitation. Giuseppe Morello graduated with the highest degrees from the University of Palermo with a Bachelor in Physical Science in 2010, followed by a Master in Physics in 2012. Afterwards, he made his PhD thesis at the University College in London in 2 years, in 2016-17, as far as I have here in the bio. And in those years, he perfected blind signal source separation, so this is called BSS, and both also non-BSS techniques, obtaining outstanding results from the analysis of exoplanet systems observed with the Spitzer and HST, the Hubble telescope. During his PhD, he also won the prestigious IPAC Fellowship to carry out a machine learning classification project on all sky surveys, working at Caltech for 6 months. He has held numerous seminars in Europe and the United States, and an invited talk to a splinter session at the IAU in 2015. In the period 2017-2020, he obtained a postdoc at COA, in France, partially engaged in the H2020 Exoplanets A program led by Dr. Pierre-Olivier Lagache. At COA and UCL, he specialized in the modeling of stellar limb darkening and other astrophysical effects, also contributing to 3 PhD theses. In 2020, he won a Marie Curie individual fellowship for the ExoMAC project, which he leads at the Instituto de Astrofísica de Canarias, together with Dr. Enrique Payet. He has recently won an Ariel fellowship at Chalmers University, where he is continuing the ExoMAC project, which is renamed as ET Café. His scientific interests are focused on the exploitation of multiple observing techniques for exoplanet atmospheres, with emphasis on the synergies between low and high resolution spectroscopy. He has also actively participated in the validation of over 24 new exoplanets and refining the mass measurements in several systems. He participates in space-based projects like Ariel and PLATO consortia, the James Webb Space Telescope Transiting Exoplanet Community, ERS program, and also in ground-based collaborations like Carmenes and Muscat 2, with important contributions to the discovery and characterization of many exoplanet systems. Today, he's talking about, as you see, the holistic approach to exoplanet spectroscopy. Thank you again, Giuseppe, for being here, and the floor is yours.
Okay, thank you for coming here, and I'm very happy to accept the invitation to present my work here today. I will, so the title of my talk is a holistic approach to exoplanet spectroscopy. I will present what I'm doing now and what I did in the past few years.
You can announce on this.
Okay, so there is a brief introduction for people that are from different fields. What I work mostly are transiting exoplanets, that are planets that pass in front and or behind their stars for a part of their orbit. and they are revealed through a flux drop when they occult part of the stellar flux that is roughly proportional to the area ratio between the planet and the star. And also when they pass behind the star, there is the flux coming from the planet that is occulted, and we can measure it. And more in general, when the planet orbits, the total flux coming from the star plus planet system vary during the orbit, and it reveals different portions of the planetary emissions with different viewing angle. And in particular, I analyzed the atmospheres. So the light that passes through the thin annulus around the planet, that is its atmosphere, to characterize the chemical composition, thermodynamics, and transport processes. Just quick numbers that I don't explain in detail, but to have an idea of what kind of precision do we need for these studies. If we consider the atmosphere as an annulus with a few atmospheric scalate of amplitude, and we want to calculate the contribution to the amount of flux occulted by just the annulus, we can measure the atmospheric scalate, which is given by the formula kT over μg, so it's proportional to the temperature and inversely proportional to the gravity and the molecular weight of the planet. And if we make this calculation for some solar system planets like the Earth, we find an effect that is below, that is in the last column of the table, and it is below 10 to the minus 6, so very tiny effect. Even for Jupiter, we have an effect at the level of 7 parts per million, I think. But what makes this kind of study possible for exoplanets is that many of them are very hot, much hotter than our solar system planets, and they are in close orbits. And so they have a very higher signal on the order of 10 to the minus 4, for example. And this is in general the photometric precision that we need. Now, if we consider pure geometry, assuming a star with a constant uniform flux distribution, this is more or less what we would observe. So a nearly trapezoidal model for the flux. But in practice, the observations are dominated by other effects, mostly instrumental systematic effect. These are some liqueurs from Spitzer that you on the top, and Hubble Space Telescope. Apart, so they are dominated by instrumental systematic effects, but there are also other astrophysical effects, such as stellar limb darkening, that makes the shape to be, or the transit not to be exactly trapezoidal, even in presence of, even in absence of instrumental noise. And so the key for extracting information from this data are two. Mostly, first, we need data detrending, so the correction of instrumental systematic effect. That can be done either parametrically by linking the observed modulations or temporal ramps behavior with some instrumental characteristics, typically pointing jitter for Spitzer or temporal ramps for Hubble data, or blind source separation method, that is something that I will discuss in the next slide because I work mostly with them. And on the other side, we have astrophysical modeling. So important effects that to account are that of stellar limb darkening, magnetic activity, so also the presence of spots and faculae. And depending on the system, we can also have a significant rotational effect. For example, flattening of the star, gravity darkening, Rossiter-McLaughlin. And in some kind of observation also, the flux from the planet itself act as a contaminant, and other technical aspects. And these are all not necessarily everything that we need, but these are the topics in which I worked in the past year. And I start presenting some of my PhD work in which I developed a machine learning method for data detrending, so to remove instrumental systematics. And in particular, the method that I used most was based on independent component analysis, which is a statistical technique to separate signals from, to separate the source signals from a mixture of them. In particular, in astrophysical observation, we have some astrophysical signal coming from the transit or the planet or the stars. It can also be stellar activity, and we have instrumental effects that are dominant in current data sets. And the objective is from a set of observations with independent component analysis, it performs a linear transform to extract the individual component. So in particular, separate the astrophysical signal from the instrumental one. And the key for making this inversion within the ICA technique is to minimize the mutual information. That is a well-defined statistical operator. And the idea is that while all the signals that we observe are somehow correlated because they contain the same astrophysics and the similar instrumental effect, the source signal, so the astrophysical one and the instrumental in itself are very different characteristics. And so they should be independent in most applications. And by using this criteria, essentially ICA try to perform to separate these components. And one particular application of this technique that I developed during my PhD was called pixel ICA, in which instead of using multiple observations of the same system, I was just treating individual pixel light years, individual pixel time series as independent observations. Even if the flux level is very different in this Spitzer image between the central pixel and the one on the bottom, you can see that they all have some hints of the transit signal at around phase 0, plus some modulations that are partially correlated. And by performing a linear transform over multiple pixel time series, we were able to extract the pure transit signal from this data. Before showing some results, I say what are the advantages of this method compared to parametric techniques. One is that it has a high degree of objectivity, which is particularly important when the instrument like Spitzer were not calibrated for the precision required by transit studies, atmospheric studies in particular. And so we don't have to guess what are the factors, the instrumental factors that determine the systematics that we observe in the data. And what was happening before in particular is that different groups using different parameterization of higher or lower order polynomials, or using, for example, Spitzer centroids or PSF amplitudes, were getting significantly different results from the same datasets. And so using a blind source separation technique somehow removes the degree of objectivity from the observer. And it is also flexible to adapt to various instrument design. In fact, I developed some other techniques, not only the pixel ICA, but for example, the stripe ICA that I don't describe now, but was specifically applied to HST WST free scanning mode spectroscopy data. And I'm trying to test some of this technique also with JWST data or with simulated data from PLATO and the Ariel consortium. Here, I just to show some of the early results that I got with this technique. Here on the left, we have a transit like you observe with Spitzer. The transit occurs around here. and all the rest are instrumental modulation that have a similar amplitude for this planet to the transit. And so they are particularly difficult to disentangle. And on the right, there is the transitinal extract from this particular observation. There were in total 4 similar observations, 2 at 3.6 and 4.5 micron. And the earlier analysis at the red point were showing a very different transit depth from one epoch to the other that were attributing either to instrument variability or strong stellar activity effect. But by doing the analysis with independent component analysis, I got the blue results, where the difference between blue and light blue is a different limb darkening assumption that I tested. And as you can see, there is much less variability between visits, and so ruling out some strong stellar variability, and also less difference between wavelengths. That some of these data were originally interpreted as evidence for methane absorption, and instead it is not evident at all from this flat spectrum here. Another example that was more challenging was the observation of a secondary eclipse, and the signal is as usual the one on the left. The eclipse, it is kind of seen here at the center of the image, but it is very hidden by noise. And on the right is the extracted one. In this case, there were 10 observations of the system plus 10 simulated datasets that were provided by the Spitzer IRAC team for the data challenge in 2015. And we tested different techniques, and based on some statistical parameters that are the repeatability, so the variation between epochs, assuming that at least in the simulation, so we are sure that the astrophysics was the same. And it turned out that the ICA technique was the most repeatable and giving the most reliable results for the Spitzer data detrending of this system. And the more recent application, just to show, I showed a transit, an eclipse, and I tried also on phase curves. And here are 3 visits on the WST 43b, which is a very interesting target now being observed by JWST. And again, here the main improvement that obtained with the Spitzer ICA technique was that, for example, for the night side temperature was highly debated in the literature. Previous measurements were giving just the upper limit of 2 sigma that are in the panel, that were also challenging to interpret in terms of physics, expected physics for this planet, while the measurement that I got are somehow at higher temperature. And there have been also other reanalysis of the Spitzer data, plus recent observation with JWST, that confirm more or less that the temperature of the planet is, or the night side is much more similar to 900, so the measurement that we got, than the very first estimates. So now just a way that I like to interpret this was that the first scenario for WST 43b was a very extreme day-to-night temperature contrast. That was even difficult to explain with physical models for the planet, while after this correction, we still have a stronger contrast in temperature, but much more reasonable based on physical models. And now I stop the part about the PhD work and data detrending technique, and I pass to the second part of the talk, discussing some modeling of astrophysical effect on which I worked, in particular limb darkening. So I developed one Python package that is open source and is called exoplanet. It is also PIP installable. And originally, it was designed just to calculate stellar limb darkening coefficients, similar to many other packages that also calculate limb darkening coefficients. But the novelty in this package was that it was optimized to give the best coefficients for transits, because some earlier study that we could discuss privately, but there is, I mean, I don't want to bore too much. Basically found that it is different if you wanted to optimize a stellar limb darkening profile from an intensity profile at given angles, or if you wanted to estimate this from transit observations. Basically because these two kind of data are sensitive to different portions of the disk. And the coefficients calculated with this code were optimized for transit observations and guarantee a precision below 10 ppm, while in other cases you can have biases of a few hundred, up to a few hundred ppms, depending on the fitting technique used. That do not depend on the stellar model, but just on the way how the coefficients are extracted from that model. And then I added some other functions. And in particular, the boats package can be used as a star planet spectral simulator, similar to Pandexo, to reproduce, for example, JWST simulated data, or it could be used for Ariel data, provided that it has the instrumental response. And also for some other astrophysical effects that I will probably briefly present in the next slides. And so in general, this package is intended to use for any kind of exoplanet mission, like Ariel, PLATO, Cheops, and James Webb in this slide. And recently, I used this package to calculate the official grid of limb darkening coefficients for the PLATO instrument, which is still work in progress, pending updates of the astrophysical models. This was obtained with Mark's model. And in particular, I'm the leader of the PLATO limb darkening working package, so responsible to deliver the final limb darkening coefficients that will be used by the pipeline of the mission, as well as gravity darkening and Doppler boosting coefficients. And I also calculated tables of limb darkening coefficients for the Ariel instruments with different libraries of spectral models. And the software Exotetis was also used, was also implemented by some data detrending pipelines like Eclipse and Cascade that have been largely used for the analysis of HST and even JWST data. As I said, another application of this package was to produce synthetic transmission spectra of exoplanet atmospheres. And I used this in several discovery paper or mass measurement paper for the Carmenes and the Muscat Q consortia, as well as from time to time for other external collaborations. And this is one of the most interesting benchmark rocky planet that we recently discovered with Carmenes and Muscat Q, that for sure will be also observed by JWST. I don't know if with our proposal or someone else, but it has definitely high transmission spectroscopy metrics. So it is one of the most favorable rocky planets for atmospheric characterization. And okay, and another aspect on which I'm working is stellar magnetic activity, and I'm leader of a sub-working package within the Ariel consortium that is called Activity Correction for Planetary Spectra. Here are some images taken from a recent paper of Alex Thompson that is based at UCL, still under review, but available in the archive, in which basically we can see the difference if we neglect the star spots in an exoplanet spectrum. We can get a significant bias that in infrared wavelength looks like just like an offset, but it has much more impact in the morphology in the visible, let's say, at wavelength shorter than 1 micron. And without entering into detail, I also experience in modeling light curves of rapid rotators, having analyzed the Kepler data of KOI 15. It is a very rapid rotator system with strong gravity darkening effects, and calculating the gravity darkening coefficients for the PLATO mission, and also modeling Rossiter-McCollum effect in observation both from space and ground, actually mostly from ground-based instruments. And another effect in which we work is the contamination of the exoplanet surface and phase bend effect that was part of the thesis of Marine-Martin Lagarde at COA in France. And in particular, this is just when we look at the transit spectroscopy, we neglect the emission from the planet that is much cooler than the star. But in some cases, it can introduce some biases. And so we quantify this effect for photometry and the spectroscopy and suggest how to correct for it. And recently, I also worked in a paper on studying the effect of temporal binning, particularly for phase curves, because phase curves observed with the Spitzer and even with JWST have an extremely rapid cadence of seconds or fractions of seconds, and they last for days. So it is a large amount of data. And so it is important to know how much can we bin them to fasten their analysis and the data storage as well. And the last slide of this is I also worked not only on exoplanet atmosphere, but also on discovery or validation of exoplanet within Muscat. In this case, I led this paper that was recently accepted and it is currently in press with the discovery of two potentially ultra-short period planets around the dwarfs. I say rediscovery because simultaneously with our paper, another paper appeared in the archive that was also including the same two targets, but we use in the different technique, and added also some radial velocity measurements that were not present in the other study. And now I pass to the last part of my talk, that is the more recent activity, even if some of the previous slides were also quite recent, which is the synergies between low and high resolution spectroscopy that I think will be very important starting from now with JWST and Ariel and PLATO mission. And I try to quickly convince you why. Briefly, when we look at the low resolution data from space, we are used to observe just some time series at multiple wavelengths that can be either photometric or calculated in wavelength bins. But the treatment is very similar. They are affected, different wavelengths can be affected by different dim darkening. You can see in the red wavelengths, it is flatter, while we have more V-shaped in UV or visible. And we have a very good measurements of the spectral continuum outside of transit. And they are mostly affected by dim darkening and stellar activity. While observations at high resolution are typically based on very different concepts. So they, instead of analyzing light years, we observe the spectra at high resolution for measuring similar, essentially the same that we use for radial velocity measurements. But we try to identify in these spectra also evidence of planetary absorption. But many other effects appear that are not important at low resolution, such as the distortion due to the Rossiter-McCollum effect, for example. But they are less affected by stellar activity or dim darkening, for example. So they have very sensitive to different contamination signal, but also sensitive to different physics. For example, Doppler shift due to atmospheric wind that is very difficult to get at low resolution. And also at low resolution, we measure just broad molecular features and patterns. Instead, at high resolution, we can identify the spectral absorption lines. So proper fingerprint of the molecule that is more unique. And one paper in which I worked was based on a debate about the presence of sodium in HD 209-458b, which is one of the most iconic of Jupiter, with exactly the first detection of an atmosphere by Charbonneau in 2002, based on HST data. But recent analysis with Espresso and also ARPS North and Carmenes, but I'm reporting Espresso because it was having the highest quality dataset. We're not finding any evidence of this absorption signal, but still they were finding some signal around the sodium doublet that was interpreted as the Rossiter-McCollum effect due to the presence of sodium in the star. And so what I did was a very simple approach to simulate using the same model, the same framework, the low and high resolution datasets, using a much thinner grid than what is shown in this illustrative picture. To reproduce, so each cell here is Doppler shifted and accounts also for stellar limb darkening. And I reproduced both transit light curves on the left, and on the right, the absorption signal from the Rossiter-McCollum signal with or without absorption that were calculated in Nuria's paper, Casas 2022. And basically, it is quite difficult to enter into the techniques, but if we look at the detail, what we found is that there exists a range of models that is compatible with both observations that are either without sodium or with sodium, but at a lower temperature than the equilibrium temperature, which is possible to have at the terminator. And also investigated the presence of clouds, because the clouds are usually responsible for dampened features in low resolution observations, but their effect is much less important in high resolution. And so we understand that they cannot be the cause of the discrepancy between the two datasets. And so this is the summary of what I just said about these planets. And it is a kind of problem, this of the overlap between Rossiter-McCollum and atmospheric signal that does not happen on all planetary systems, but we identified a few dozen of planets which have overlapping signals, so we can apply the same Bayesian framework to their analysis. And one more recent application that I mentioned is on synergies with JWST data. I'm still a PI of the JWST Transiting Exoplanet Community Early Release Science Program. We measured the most complete transmission spectrum of an exoplanet that covers from the visible 0.4 micron up to 5 micron, identifying different molecules. But there are still, despite the super high quality of this dataset, there are still some doubtful results. For example, hidden in this dataset around 3 micron, there is a small, around, to show here. Well, the yellow feature on the right, around 4 micron, that is a small bump attributed to SO2. But as you can imagine, given it is a small bump that you observe in a spectra with multiple bumps, it is difficult to be totally sure that this molecule is SO2. It is not expected at chemical equilibrium. So the modelers hypothesize some photochemistry to explain this detection. But still, I submitted an ISO proposal to observe this region with CLIRES at higher resolution to actually identify whether it is really SO2 by using the cross-correlation technique. And another thing is the CH4 methane that it does not have a very strong bump at around 3 micron, the light blue molecule, but it can still be identified an upper limit at higher resolution. And one example of this is that, for example, in one of these data sets, there was CO was not identified at the original resolution analysis of the JWST data, but was later identified with the cross-correlation technique. So it is really possible that these observations are complementary and can help to determine the full chemical inventory of a planetary atmosphere. So I summarize now what I presented in this talk. So I worked on development of data detrending pipelines, in particular blind source separation method with application to Spitzer and double data up to now. And some experience with astrophysical modeling, in particular stellar limb darkening, magnetic activity, and I'm responsible for 2 working packages for the PLATO and Ariel missions on these 2 topics. And other application of a software that I developed and is open source. And the most recent project that I'm developing between ISE and Chalmers University on the synergies between low and high resolution spectroscopy with immediate application to JWST early release science data, but will be very useful also for the Ariel data for similar reasons. Okay, that's it. Thank you for time.
Thank you very much for this talk. So now the talk is open for questions. Please, in the room, if there is any question.
Thanks, Giuseppe. Okay, any questions for Giuseppe now? If you don't have any in mind right now, I have thousands. I have a list here, but okay, thanks. Giuseppe, could you go back to your contribution to modeling of astrophysical effects? In particular, could you explain a little bit more what you did for modeling rosothermal Laughlin effects in your work?
Yes, so this is an example. We have a star with the noun Viseni. So the 2 hemispheres here are Doppler shifted on the blue or red side, and there is also included the limb darkening effect. So basically, I take a stellar spectrum template with result in angularly result, so that it accounts for the spectral limb darkening. For the limb darkening, I measure the projected velocity of each cell and apply a Doppler shift. And by summing the contributes from a large grid, I think at least 300 by 300 pixels, but it would be better even more. It becomes computationally challenging. Basically, I get a spectrum that includes the rotational, the impact of rotation. And then when a planet passes in front of it, I occult some of these pixels. In this study, I don't consider the planet just as a simple circle, but I also account for the atmosphere. So depending on, so the planet, so some pixels are totally occulted by the planet, some others are occulted or not occulted depending on the wavelength. So this includes for the atmosphere. By doing this study, basically, it is important whether we stay in the stellar reference frame or in the planet reference frame. So we have to bring all spectra in the same reference. It is not very important at low resolution, but it is important at high resolution, where, for example, this is on the right panel are the spectrum, so the F in flux during the transit, so some over the full transit from the first contact to the last contact point, divided the out of transit flux that is not affected by the planet, and -1 in percentage. And if considering that the simulated star contains sodium, the red signal is just the signal that we would obtain due to the Rossiter-McLaurin effect. And then if we assume that there is some sodium in the planetary atmosphere, we start getting a dip at the center, which are the other models. But if we assume solar abundances and equilibrium temperature of the planet, we will get the orange dip that we would have detected with espresso. Adding clouds does not change much. I don't know if I can point it, but it would give the gray point. It is a very little difference, but but it is possible that at a lower temperature, that are definitely possible in the atmosphere because the temperature is not constant with the angle, and we can have a much smaller peak that if we compare it with the noise in the espresso data, maybe not detected. Also because there have been some other modulations due to the instrument that were also removed, so it can be easily masked, this signal. Now, I think that one question that you may have is that the amplitude of the signal does not seem to match at all the espresso result. And this is actually true. We decided to leave this like this because making more simulation is very, very time consuming for now. But if you try a slightly different atmospheric model, for example, a slightly different stellar model, for example, without the local thermodynamic equilibrium assumption, we observed it had deeper sodium lines. And just by having deeper sodium lines, you can change the amplitude of the signal. Also, link darkening can have a small effect on the signal. So basically, what we investigated in the study was the shape and the variation on the shape due to the absorption, but not the absolute amplitude. But of course, having the correct spectrum with the true absolute amplitude would give more, probably some more constraint on the abundances. Another thing is that, for example, here I presented different temperatures, but we also tested the different abundances. For example, can we assume that it is not lower temperature, but it is 1/10 solar abundances? And in general, with very extreme example, yes, it is possible, but essentially this feature is much more sensitive to temperature than abundances. Changing by 1 order of magnitude was not significantly affecting. Here I'm talking of abundances in the planetary atmosphere. Was not significantly changing this signal. And it can be applied on different lines, for example, magnesium.
What is the range in wavelength where you can apply your simulations?
So this really depends on the spectrum that on the stellar spectrum. As long as I have a stellar spectrum, it can go to the ultraviolet or far infrared. It doesn't matter. In general, this effect is important for atoms, so or ions. So I expect visible wavelengths, and it's not. It's not easy to obtain, let's say, these wavelength dimensions.
Okay. Any other questions for Giuseppe? Frank?
Thank you, Giuseppe, for your talk. I'm very interested on your exoplanet package. I was wondering which are the limits that you are using in the range for the temperature, metallicity, and the wavelength that you are using.
Okay, so there are different libraries. So there is one very old Atlas library that is the most comprehensive, go from low temperatures up to 50,000 Kelvin and gravity. But I would say, given it is old, maybe it is not the most accurate. But A good one, I think, is Phoenix libraries that cover from 2000 something up to 12,000 Kelvin.
Okay, so if I understand well, you can choose the library when you are computing the inductance in your calculator. Okay.
Yeah, but I have a library, so but it has to be a library that is for now. It has to be a library that is already implemented. So there is either Phoenix that has a large coverage, or there are also Stagger models 3D, but they cover only 4,000, 7,000. I plan to include new libraries when I have them. And actually I have some that I could add now. And one other objective that shouldn't be difficult is to let the user to use their own library. But this is not implemented yet. Okay, this function.
Thank you.
But sometimes I use it just because I know I wrote the code and so I know how to trick it. I use it with my own library, but it is not a user-defined function. So if you need to do it, I can tell you how to do it.
You have to make them public as well.
But it is not in the package.
Thank you.
Hey, any other question? I just want to remind you that Giuseppe will be here all day. Tomorrow you are leaving
In the morning.
So probably, if you want to talk to him or you want to join us for lunch, because we are going for lunch, you are welcome, and we can discuss all the very interesting topics that he has brought up today here. Sorry for those that are in at home that cannot join us for lunch, but any of you, if you want to come, yes, Christine.
I'd like to ask how it's new for what you have to do, use your machine learning approach or content analysis with other spectra coming from the instruments to your type of coordinates or the James Webb in spectrum. How much you have to tune on what you do?
Okay, so let's say that up to very recently there was not a proper package. So one of the limitations was that independent component analysis has many different algorithms, and I noted that not all of them were sufficient. So I was using an algorithm that only had Fortran or MATLAB version. But recently a student in France has wrapped it into a Python. So this can be available and it is relatively easy to use. But at this moment, it is only designed for pixel lectures, so photometric observations. I mentioned that there are some possibility to use with spectra, and basically this would require writing a function to read the data, process the data, and then what we have now is basically the function that if you have the time series or spectra, because it can also receive spectra as input, to apply the transform. So now this is fast. The other parts are first the extraction of the time series or spectra, and second the MCMC fitting that is not automatic. So, but the transform is very fast now. It does not require any. It is based only on open source software, not MATLAB, and typically even for a very long time series with the million data points can take a few minutes. So it's usable.
Manuel, sorry.
Right. Oh, thank you very much, Giuseppe, for the nice talk. One question about this one. You are essentially, if I understood you right, essentially questioning the first detection of the atmosphere made by David Charbonneau on sodium on this exoplanet. So do you think that what really observed can be explained by effects which are not really the presence of sodium? What is your opinion? I mean, at the end, is it there sodium or not in that atmosphere?
Yes, and I show the result, because this is a very good question. I think that the current data are not totally conclusive. We can definitely rule out sodium at solar abundances and equilibrium temperature. And there are some possibility that other effects that are, so for example, if we let fit of the same data with free limb darkening, with the significance that was at 4 sigma can decrease below 3 sigma. So there is a possibility that there is no sodium at all, but the most likely solution that I have from the current data is that I think that probably there is sodium, but with some dampened feature and with a temperature at the terminator of 700, 1000. Let's say that this is the best likely solution that I get. But it is also consistent with no sodium. So,
I have a further question. Yeah, it's about your last point about the using the low and high resolution.
Yeah.
Do you plan to do retrieval of abundances from the combination of both data?
yes, okay. I think that I have a slide. Okay. Yes, this is some work that I'm doing now that is difficult and may take some time, but on not using cross correlation just for detection of the molecule, but also for determining abundances. And there have been some recent papers that also were making cross correlation with a model with multiple molecules, for example. And yes, the idea is to implement some proper cross correlation retrievals. You know, there are some. It is not fully original. There are some trials now based on grids, but not a proper Bayesian framework. And this is what I would like to implement now, in particular with Taurex, through the UCL people that are managing the Taurex code. But I no idea now how long how complicated this can be. I discussed with some of them, but it may take months, 1 year.
Do you mean the correlation by itself or just with something like
not to
minimizing
to have it implemented in the Taurex, for example, as the proper retrieval? Because, for example, now what I'm exploring is, in some cases, different models have an impact on the peak. In other cases, we have some effects on the tails, but I don't know if it is how to interpret it, essentially. So I'm running some grids of cross-correlation retrievals for testing this effect. Once this is fully calibrated, I don't think that the implementation in Taurex will be very, very difficult. But I'm not the person who is implementing it actually in the package. So,
okay, good, thank you.
I mean, I'm not an expert on this field, so my question refers mostly with the method you use the whole time, mostly is the independent component analysis. Is this the same as the principal component analysis method?
okay, no, but it's a good question because many, so it is a frequent question also for this one. I had some slides, I think. But essentially, the main difference is that principal component analysis, okay. Yeah. So they are both linear transformation of the observations and try to find an orthogonal basis of components. But principal component analysis try to find uncorrelated components, which means that the mean value of the product is equal to the product of the two mean values. And these just use up to second order statistical estimators. While ICA use a more stronger concept of in which any function of the two variables are uncorrelated, and this is used. This requires higher order statistics. Then, so this is very qualitative difference. And there's
That's enough. Thank you.
more detailed mathematics.
Thanks.
Okay. Oh, yes.
Thanks, Giuseppe. Maybe it's a naive question, but the technique that you developed to remove the RM effect that I never know how to pronounce roughly, whatever effect, but from espresso data, right?
Yeah.
Is this technique easily, I suppose it's not easy, but to apply to other cases? Just, for example, put in as input another star.
Yeah, yes, I did not use, for example, the espresso response for making this. It is just one stellar spectrum, and
This is flexible.
yeah, yes, this is. The complicated thing is that you need a very thin grid, spatial grid for the star, and if you have a high resolution spectra, it is time consuming, but especially RAM consuming, more than time consuming.
And the technique, is it available? Because I think there's a student, it is available for the espresso community.
Okay, no, I did not make a package for that. I have some script that I could pass. I pass to some people the script, but it's very basic. It is not complicated, but yes, I did not make a proper package. I think it is easy
But
to
you can
use.
share.
Yes.
So related to this, you say you need a specific intelligence spectrum for this.
Yes.
Our high resolution.
Really, high resolution. So it can be run with any resolution that you want. Of course, it has to be a resolution that is enough for the instrument that you should be a little bit higher. Let's say at least a factor of 5 higher than the resolution that you want to analyze.
Okay, thank you for all your questions. I don't see any more questions here in the room. No questions online. So, okay, we thank you, the speaker again.
Thank you very much.
Not related to this, but in 1 hour we have the launch of JWST.